Okay, let's get started, everyone. We are audio-visually active. Fantastic. Okay, well, thank you very much for coming, everyone. It's a real pleasure today to introduce Pedro Lopes from QuEra. Pedro is originally from Brazil. Did his both undergraduate and graduate degree at São Paulo University. Correct? Huh? Campinas. In the state of São Paulo. Okay, great. And during that time, he also had a fellowship to go to UIUC, and it became a theoretical physicist as a result of that. So this is a talk that is not about theoretical physics. There's a little bit of theoretical physics going on, but it's really about the development of a remarkable new technology that is actually happening across the river. In fact, you could probably see where it's happening, right? It's either there or there.
We'll make an attempt later.
Huh?
Yeah, it's kind of there. Yeah.
Oh, I'm sorry, it's up there. Yes, okay, it's up there. Okay.
It's there, yeah.
Yes, but yeah, okay, but the actual science actually happened over there across the river, right?
But science happens in both ways.
Okay. Yeah, so there is a revolution going on at the moment in computational technologies, okay? We're all used to these boxes here, which are basically boxes full of switches. Switches are either on or off. The technology that Pedro is going to tell you about today is with switches that are on and off both at the same time, okay? So these things are in coherent superpositions of being on and off. And the things that we're going to be looking at, you could have like, the Google and the IBM machines are all superconducting qubits that are very difficult to work with and manipulate, and they're all on a chip. These things are atoms, the simplest thing you can imagine. They've got a few electrons in them, but they're rubidium atoms. But they're atoms, and they're individual atoms that are doing your computation. Okay, that's the bottom line. Okay, they talk to one another and produce entanglement, and we're going to hear how this is done. And so, without further ado, Pedro is going to tell us about this. Thank you.
Oh, question then. Thanks very much, everybody, for the invitation and for receiving me. I want to tell you a little bit. I guess I was tasked with bringing you a little bit of information on who is QuEra Computing, what our company does, and how the technology works. And I will try to spice it a little bit in the end with how we have been engaging with entities in the state of Massachusetts, in the Commonwealth, to develop the ecosystem, the quantum industry ecosystem in the area, which we believe that's going to bring success to our young generations, or not so young generations, our companies that are coming to be, and our companies that are established. So the success of this ecosystem is very important for us because it's going to be part of our success as well. So the starting point of this conversation, again, as David was mentioning, is the atoms. So if you are looking at this figure here on your right, you are looking at these kind of green dots, right? And these green dots are individual atoms of rubidium. So you're looking at one single atom of rubidium at each point. So what we are doing really at QuEra is kind of the aspiration of what classical computers would like to do if you could make a transistor that is a single atom in size. Turns out you can't, right? But if you're doing quantum computing, turns out you can. So what we do is to hold atoms in free space using laser light. We'll talk more about that. We position them according to user specifications, to the interests of the needs of the user. That those needs might be scientific, these needs might be on the physical sciences, they might be on the computational sciences, they might be in the engineering space, and we use them to do calculations. So we can control these atoms precisely one by one in real space, both their geometric positions and also the energetics or the dynamics of those atoms, and we can use that to do calculations. So we're really talking about atomic level precision at scale. So this is awesome. To start, we'll talk a little bit about QuEra as a company. And this photo is from a couple years ago. We were about 20 people, 20 some people at the time, and by now we are about 80, a little less than that, but growing up very, very fast. In fact, if I look at this photo, there is a fair amount of the team that has already changed and moved to kind of very illustrious positions, and many others of them stayed, like me, and we continue growing the company. And now, the most important reason why I'm showing this slide is not to kind of rub fancy stamps on the corners, because I don't care about that so much. These are great partners to have, but the reason is for me to remind you that we are growing very fast. We are actually hiring considerably, about doubling in size in the next couple of years. We are hiring now. So if you happen to be an electrical engineer looking for an opportunity, a mechanical engineer looking for an opportunity, a computer scientist looking for an opportunity, a physicist looking for an opportunity, a business person looking for an opportunity, we are really hiring all across. So do reach out because we have like a big mission to deliver on, and we are really, really looking to grow the family. So what does this family do? Right? Every family is equal, and some of them are, you know, the story. In this case, the family, what we see is that we are a tech translation engine, right? So sure, quantum computing is the specific topic, but the way that we operate, or the aspiration here, is to work as a tech translation engine, right? So there's a lot of development that happens at universities. Locally, we have plenty of them. Again, Harvard and MIT are the kind of part of our core DNA because that's where we spun off from. But we work with many of them. We have collaborators here at BU. We have collaborators at UMass Boston. We have collaborators in UCLA, in Chicago, all across. And we are helping translate the technology, particularly technology from the quantum space, into kind of university research, university demonstrations, into technology demonstrations, and those technology and demonstrations into commercial products. In the process of doing that, we feed back the pipeline, right? So we learn how to take something that looked like an experiment and make it kind of more stably. In that process, we create some devices, some components, some parts, some IP that we can feed back into the university so the university can do things faster, more stably, right? It's always good to remember that for those that are familiar with quantum mechanics, doing experiments to violate Bell's inequality 15 years ago or more required a whole PhD thesis, and nowadays you just go online and type a few commands and boom, you do that in a few seconds. So this means that the next researcher doesn't need to build a full experiment to do that. You can ask the next question. So this pipeline is very important to both advance science and advance commercial products. Of course, we're a commercial company, so being able to commercialize these products is extremely important for us because that's what allows us to also feed back into our aspirations and then help the gear rotate. So to make sure that this is not just words and that you understand how this actually happened, I think that it's worthwhile taking a brief moment to just look at the history of QuEra and some of the achievements that we have done. Back in 2017, there was an experiment being built at Harvard in the basement with Michel Lukin's lab, and that had like about 4-ish students, grad students, where they were actually operating the largest quantum computers. They have about 50-some qubits, and this was actually before Google was declaring these quantum supremacy experiments that they did shortly after. So a huge team at Google was actually competing with a team of like 4 students at the universities locally here. And we saw that the technology was advancing so fast and the demand for access to that technology was actually growing among collaborators that QuEra was founded. That was basically the short story of it a couple years later. 2021, Harvard Lab was doing 256 atoms demonstrations and experiments. 1 year later, 1 year and a half later, we had such a machine online. So I think that this is a great kind of reason of pride for us at QuEra. We are really happy with this achievement because in 2017, there were 4 people in the world that could do experiments in this kind of system. Today, any one of you can. Any one of you. So It's on the cloud. It's a public cloud. It's not an open cloud. Anyone with a credit card can run, but it's quite affordable. And there are many more steps to really kind of make this a democratic access to quantum computing. But this is a great first step for us. And it took us 5 years. And if you look at the moments when the prototypes that were operating like Aquila, that we are going to talk about this computer a lot today, came to be done at Harvard, and when we put it online, it's barely 2 years. So this is really, really, really fast translation from what happens in an academic lab into the broader world. Not only that, like a few months later, last year, there was a demonstration for high fidelity entanglement gates with neutral atoms. So neutral atoms have been seen before as a kind of a dark horse of quantum computing. So it's a technology, it's there, everybody sees it, maybe it looks promising, but there are many doubts. People are saying, oh, okay, but your fidelities are so low, you will never be able to get higher fidelities, to which we were saying, we are not in a rush. There are so many other things that we have to do than kind of polish fidelity. So we have to work on other things before that. When it came the time to polish fidelities, we polished fidelities. And voila, we can do entanglement at fidelities that are basically comparable with all the other technologies. And upon realization of those kinds of demonstrations, QuEra put our engineering team to work, built some special controller systems and cameras, sent it back to Harvard, and less than a year later, boom, here we are doing kind of world record operations with logical qubits. So we have been operating, kind of doing demonstrations with 48 or over 40 logical qubits, which is something that is really at this stage of kind of the forefront of the technology. So this feedback loop, both one way and backwards, is really a realistic thing. It's really how we operate. And not only with Harvard, again, there's collaborations going on with many other universities. Compiler systems that come from Chicago, from Los Angeles, are finding their way into our systems. Meanwhile, we are informing them what are the actual requirements from our systems so that they can do their research more close to our systems, and so on and so forth, which is really our secret sauce, right? Or the secret sauce ingredient number one. I tell you the ingredients, but I won't tell you how to cook, right? But ingredient number one is this idea of co-design. Right? So you need to put like a theorist sitting together with an experimentalist, together with an engineer, together with business people, and really kind of co-design technology, co-design the company, co-design basically everything. Right? Like, here we talk about technology because it's the kind of I guess for this audience is the most important piece of information. But if you want to do quantum computing today, you have to remember that quantum entanglement is a limited commodity, right? It's not everywhere. You can't just run a little bit, throw something out of the window. That doesn't fly, okay? So if you want to do quantum computing that works, you really, really need to polish your applications, your software, your algorithms to the machine that you are using. That's our philosophy. That's how we got this kind of demonstrations so far. And there are plenty of items, right? Like from the algorithmic pipeline, you can see that there are error correcting code choices, there are compilation choices, there are gate design choices, there are protocol layouts. So if you're optimizing an application to run on a neutral atom computer versus a superconducting versus an ion trap, the design parameters are different. The requirements, the speeds are different. The flexibilities are different. And on the other side, your hardware, what are the requirements for speed of operation, the connectivity between your qubits, the parallelization that you can do. So these are things that once you put them side by side and really know what is possible and what you need to develop next, you really speed this development up, right? So otherwise, you'll be doing here what you want to do on one side. Once you're ready, you show something, and then the other side, oh, okay, could have told me before, right? Because now this is important information for my next step. So operating close and designing simultaneously is very important. The secret sauce ingredient number two is that we are really hyper collaborative. We have been working with academic partners through the country, through the world, really. We have been working with commercial companies through the world as well. And we have been working with governments, both local and international. And we think that this attitude to kind of connect with people, talk with people, find common ground is really, really important to keep things going. That's the motivational part. Okay, so from now on, like, okay, now we know what is actually at least our philosophy a little bit, or at least a little bit of my vision of our philosophy. From here on, I want to go in and talk about the hardware itself. Do you have any questions about this? Yeah. Who is my customer? So, no, it's not just academia. I'm joking, right? We have had users from BMW. We have had users from BP, the British energy company. We have had users from DOE, from national labs. We have had users that are local universities. We have had users really throughout. Consulting companies, Deloitte is a big developer on us. So we have really like a broad spectrum of different groups that are interested in using our systems. Sometimes it's optimization of a problem. Sometimes it's to do like a proof of concept to see exactly like what's my opinion about this technology at this moment. Is it like time for me to invest more? It's time for me to kind of hold a little bit and understand when it will be the right time to invest. There's going to be times that's going to be, I want to develop more science. There will be situations where an organization across the world might be interested in developing the economy of their region. And they realize that putting a quantum computer there allows them to, first of all, right, like I was telling the students earlier, right, like what's the first thing that happens when a quantum computer arrives in your home? Like you look inside, right? So you see new technology that you didn't know before. You are gonna have to operate that thing, so you're gonna hire people. You're gonna have this thing in a prestigious space, which means that around that space you're gonna have economic development of the land. So there are many reasons why you'll be wanting to access. You might be able to have other companies in your area that wants to develop components for a quantum computer to be able to test those components in this given machine. So there are many reasons why you have kind of an engagement with different users. Some of you should not. I guess you should differ users and customers, right? Sometimes users are customers, but there is like many. If I call customers, also incorporate partners, groups that are interested in working with us to develop value for them and for the company at the same time. There is really, really a broad spectrum of what they look like. Cool. Let's keep going. So I was asked for a brief tutorial on how a neutral atom quantum computer works. So here we go. Like, take a deep breath, don't breathe. So key features, 4 of them right now. Of course, neutral atoms. We are not building this with ions. We are building this with atoms. Qubit shuttling, so moving atoms in free space, moving them around, literally transporting them in real space. Parallel operations, so don't operate on things one after the other, but rather in parallel, together at the same time. And finally, this idea of zoned architecture. So I'm going to touch on this again, but your computer, this thing here, is not monolithic, right? When you open inside, right, you don't see like transistor from one side to the other, right? There are functionalities, right? There are regions of this computer that have different functionality. Some is memory, some is random access memory, some of them is processing, and having this kind of capabilities being made by design allows you to optimize the use of each of them and make sure that they are orchestrated rather than conflicting or interfering with each other. So that's some of the key features. What is a neutral atom quantum computer? Well, neutral atom quantum computer is something more or less like this. We use rubidium. If you don't remember where rubidium is, it's over there in the first column of the periodic table, kind of in the middle-ish. First column, for the chemists in the room, you know, 1 electron is free. Quacks like hydrogen, feels like hydrogen, smells like hydrogen. It's not really hydrogen, but it really, really feels like hydrogen. And 1 electron to play with, so that's more or less what you're looking at the top. These electrons will have different energy levels. Some of them are close to the ground. Some of them you can have an interaction with the nucleus and they split it into what we call the hyperfine structure. Other energy levels are very large. They're very excited. You give a lot of energy to your atom, in our case via lasers, and that makes the atom kind of puff up. And when they puff up, they get very polarizable. Fun fact about physics, right, is that the polarizability of a system is proportional to the volume of the system. It's very intuitive. If you want to bring charge to one side and push the other charge to the other side, if the material is big, well, I push a little bit, they're far from the other side. But if it's small, they'll probably be attracting quite strongly. That's the bigger it is, the easier it is to push charge around. And then with this, you can make them interact. How do we hold them in space? We hold them with laser light. My famous joke, if you have seen me say this joke, I will say it again, I'm sorry, but a laser is not like lightsaber, right? Like lightsaber is straight, but laser has a waist, right? A waist is what we call the focal point. And the focal point then happens to be sticky. Like biologists like to use that to hold cells. Sometimes they kind of even do surgery inside of the cells. We use to hold it to hold individual atom. Any dielectric can be held by laser. It's not too hard to get an intuition why. You can think of a little bead of crystal, and light is going through, and the laser kind of has a profile of gradient, right? It's more intense in the center than on the side. So if light goes through a bead, it's going to kind of, if the bead is a little to the side, it will kind of, the light is going to go in and refract to one side. The light from the other side of the beam is going to reflect to this side. But because there's more intensity on this side, there's going to be more light going that way, and light carries momentum. If there's more momentum going in one side, what happens to the atom? It goes in. It has to compensate. And that's the kind of the semi-classical analysis for this. So we hold the atoms in free space, and that's it. These atoms, they live in 2 dimensions, and we can really place them in many, many different ways. So the baseline for how the computer works is a few different elements, including the SLM. You might be seeing it over here. Can you see my mouse? Yeah, you can. Right. So the SLM, the AODs, and well, basically the other elements. So the SLM, my next joke is that in AMO we like TLAs. In atomic molecular optical physics, we like 3-letter acronyms. And turns out that the secret of 3-letter acronyms in AMO is that if you read them backwards, it makes sense. So a spatial light modulator modulates light in space. It's as simple as that. Like it modulates, it creates shape, it creates patterns in space for light. Right, so it's a little reflecting mirror that is programmable. Actually, it's an active optical element, and it's a liquid crystal. So you apply voltage, you can make these little sticks, rods in the liquid crystal move, and that imparts phases to the beam. So the beam hits this thing, and it reflects with the Fourier transform of what you were putting there. And that Fourier transform can be a square lattice. That's what you're seeing here. Right, it's just by creating the phase of the light spatially. Then you have the AOD, next 3-letter acronym, right? It's the acousto-optic deflector. It deflects optics via acoustics. So it's you send an acoustic signal, and it's going to deflect light. It's just going to be a crystal in there that's going to be kind of piezoelectric, and the light's going to pick up the phonon from that and basically move it. So you can steer the light. So this way, we can take atoms, we can place them somewhere, and then we can reorder them, move them, pick up them to move them around until I put them in the right place. That's the baseline. So, by the way, stop me if you need. Let's look again. We're going to go through those 4 features a little bit in detail. So we're talking about atoms and scaling and putting them in place, right? So, estimates today is that 10,000 plus physical qubits can fit in a single system, probably much more than that, without needing to kind of connect different devices. And these guys, because we can move them around, we can have all-to-all connectivity between those qubits. It's not like once you printed this laptop here, the chip, it's printed, you don't choose. But these atoms, I can move them around, so I can reprogram who talks to whom. Proof that it is possible to at least see from an optical objective 10,000 laser spots. So these are some works from Chicago and Princeton, showing that you can see the laser spots and fit them in an objective. Those have no atoms, but this has atoms. This was done by some groups in Germany last year. Yeah, about last year. where they were loading 10,000 atoms in a single system and starting to order them. So that's pretty good. The wiring of these systems is all kind of laser. You can multiplex that, so you don't need to have a bunch of cables. So that's actually very, very important to not have too many cables. We'll probably revisit that as well. And the fidelities, as I mentioned before, they're pretty good. So neutral atoms are pretty good because of those. Some of the reasons why neutral atoms are good are those. Right? Again, I'm not here to judge which one is better or worse. Those are some of the advantages. This ability to move atoms around also allows us to do very efficient operations. So if you may have heard that to do quantum computing at scale, you need to do error correction. To do error correction, you need to encode information of of 1 qubit into many qubits, right? Many, in our case, many atoms. And if you are going to print that into a solid state system, you have to decide ahead what is going to be the way that you're going to encode that information. You're going to design that chip according to your needs. You're going to print that chip many, many copies until one of them works. And then you're going to be maybe unhappy because maybe you made a bad choice of code. With the atoms here, it's great because you can empirically test. If you change your mind, you didn't like what you did before, just move the atoms again, and in a few milliseconds, you get a new try. So this is pretty good. Another thing that you can do here is really to do parallel operations. In particular, there is a type of information manipulation process with logical qubits that's called transversal gates. So you need to entangle two qubits. They are patches of qubits. Somehow you have to transfer information from here to there. If your system is stuck in place, you have to sort of go out of your patch, transfer that information somewhere until it gets to the other side. There's a process for doing that called lattice surgery. But if you can move your atoms, all you can need to do is move them side by side, shoot one laser light, and now these atoms are entangling 2 by 2 in each pair. And boom, you're done. Now, it's not every single operation that can be done that way, but the fact that you can do this allows you to have a lot of savings in time and coherence that at the end of the day is very important because coherence, quantum coherence is a limited commodity, right? It's not free for all. So good, efficient operations. So we went from atoms, we went to shuttling, we went to parallelization and the computing architecture. So this is the story from before, but again, if you look at your processor, it's not really a homogeneous monolithic structure. If you look inside of these things, they have kind of different needs and different uses. They're functional. Right? In particular, if you use GPUs or if you use FPGAs, this is going to be very, very evident. We see no reason why quantum computers should not be the same. So when you think about computing engineering, computing architectures, you probably want to make sure that you use your resources the best possible way. And here, so far, what we have been thinking is that there are regions for storage of memory. You want to keep the qubits there undisturbed while you operate somewhere else, your entangling zone. And as you entangle them somewhere else, they don't really change. They don't really mess with the information that you store in the memory. This is important because quantum computing is kind of paradoxical, right? Like you want to keep the best coherence possible. So how do you keep coherence very well in a quantum system? You don't touch it. You don't leave it alone. Right? The coherence is going to be great, right? But you need to operate on them. So that's the paradox. One way of solving this, well, don't operate on them at the same time everywhere, all at once. And then we have like a readout zone where you can also measure and look at these things without interfering with everything else. This is possible because we can move the atoms. We're going to talk a little bit about this. How do we entangle atoms? We entangle them via this thing called the Rydberg blockade. We're going to look at this very briefly, but the point is that if you give local energies for these atoms, you can split the energy space of them. So these are just a kind of 2-qubit system. So we have 4 states. And the point is that there is always an interaction whenever 2 atoms are excited. They are big. This is a van der Waals interaction that happens because they are very polarizable. So that are R states there. These are R states because both atoms are interacting. This state gets an extra interaction from this van der Waals component. And van der Waals interactions, they decay with a power law in the distance of the atoms. In this case, distance power 6. Now, because they interact with a distance to power 6, if you put them close together, now is a moment of a lot of tension. Right? Like if you put them together, they ooh. Right? I'll do it again for effect. Like ooh. Right? So you push away one of the states from the Hilbert space. It's actually not that far, but it's from with other energy scales, you really can't access it anymore. And now you have states that have only one of the atom excited at once. This is called the Rydberg blockade. And because only the excitation of one atom influences whether the other atom can be excited or not, you can use this to generate conditional logic. Right? We won't go exactly on how we do the gates because that can be complicated, but intuitively you should appreciate that if one qubit in a given state affects what happens with the other qubit, you probably can do conditional logic with that. You can do entanglement gates with that. And that's what we do. This entanglement is pretty cool because we can transport it. Right, so transport means what? Means I can put this atoms side by side. Remember that distance is how we entangle them. So we put them side by side, shoot a little laser, they entangle. We measure the parity of the state, and you figure out that it oscillates in that way depending on the final phase that you're putting on the system. And you're happy. This is pretty solid. Now you do the following. You take these atoms and you pull them apart. This is real Alice and Bob. Like if you have been doing quantum information, like Alice carries a qubit, Bob carries another one. This is like Alice is on the top, Bob is on the bottom, right? And you measure again, boom, it's on top. So you can move these atoms apart. You can let Alice go away, let Bob go do whatever he wants. And when you measure your two atom parity, you are still good. It's not so simple. There's a lot of kind of, again, more secret sauce on how you make this happen, but it is possible to do it. Not only it's possible to do it, it's possible to do it inside, basically, in a distance that is comfortable with the time scales for decoherence in your system, like for thousands of gates. That's the expectation here. Good. Why would you do that? Well, first of all, if you wanted to do entanglement between, well, not only entanglement, you're going to exchange the quantum information between the qubit that is on the top and the qubit that's on the bottom, and you only have first neighbor connectivity, that's the circuit that you have to do. You may or may not be familiar with quantum circuits, but I think we can all agree that this thing here looks complicated, right? If I can move my atoms, that's what I do. I take one atom, bring it down, take the other atom, bring them up, done. No bunch of gates. Each of these gates costs, you can imagine. So this is pretty cool. Reason number 2 why you could do it. It's the controls budget. If you look at the number of controllers that you have on your computer, well, you're talking about billions of transistors to thousands of external controllers. If you look at this technology that I'm not going to name, you realize that every qubit takes about 3 cables to control. And these cables, they are very high performance and they require like hundreds of controllers in order for you to operate because of crosstalk, because of a bunch of other things. If your controllers or your cables costed $1,000, there are estimates from DARPA that say that you need basically 10 million qubits for a utility scale quantum computer. So there's no way for this to cost less than $20 billion. And spoiler alert, it costs much more than $1,000 per wire. So what we are doing is play with these AODs, in which a pair of AODs can control a patch of qubits. You basically multiply tones, and you can control patches of qubits together. And in this case, we are talking about having kind of really order 10 controllers to operate really, really like a lot of qubits. And because we can move these atoms around, we don't need to shine this on everybody at once. You shine only on what you're moving, what you need to operate. So this means that 1,000 qubits can be controlled with a pair of AODs. 1,000,000 qubits can also be controlled with a pair of AODs. Maybe it's going to be a little slow. Maybe you want another pair of AODs to parallelize. But matter of fact is that you don't need to necessarily increase too much the number of controllers before you do calculations. Put all ingredients together, you see exactly what I was mentioning before, right? So we have been doing pretty large explorations with logical qubits. So I want to emphasize this has been work that's being led by Harvard, but definitely with a lot of collaboration and contribution from QuEra. And here what we are doing is operating this 832 type of code. It involves basically encoding your logical qubits into these boxes, right, of 8 other qubits. And you can move them around, and every time you see a little ellipsis, it means that those qubits are being entangled. And in fact, it's kind of fun that if you pay a lot of attention, I'm going to run again. In the beginning, you see that the atoms, they kind of, you have 4, and they go like a boom, then they go boom, and then they go, oh my God, I did 1, 2, and then they kind of flip, right? And that's basically the box. You think of a box, you project here, project there, project in the other dimension, right? So let's look at it again. It's like boom, boom, boom. It's just that the box is flattened into a rectangular patch, right? So it's kind of fun that if you stare enough at this, cross your eyes a little bit, you see that what you're doing, it kind of makes total sense. Cool. What's up? That would be a laser shooting entangle, like a light that entangles them. Yeah. They remain entangled.
They remain entangled?
Yeah.
Yeah, okay. So it's the Alice Bob paradigm.
It's the Alice and Bob thing.
Okay, and then they re-entangle with something else?
Then you can entangle them. Now you have a state that is like complicated, entangled state, and now you can put the other qubits in contact, and that state keeps.
So you can expand the entanglement right across the entire network. I see.
Exactly. What's up, Rich?
Translate. This box has 8 qubits, right? Can you give a logical gate level description for each of these operations?
Those are always CZ transformations, and I think that it's too small here to see, but they are CZ and sometimes CCZ transformations that you have to operate. So
they're 2 qubit logical gates.
Yes.
But then,
or 3 sometimes. Yeah.
Well, yeah, that's my question, because to get a complete set of gates for universal computing, you need a 3-gate operation.
You could do topology, but if you have kind of universal rotations plus kind of some entangling gates, you can actually do universal computation.
Oh, you don't need a 3-gate operation?
You don't need a 3-gate.
Oh, my mistake. I have to go back and read the text.
Anatoly.
So if you want to keep entanglement, basically Hamiltonian should be 0 when qubits are decoupled. To what degree this 0 is 0? Like how well you control 0?
So 0.
I'm just curious, so if you translate it to time, like.
So the reason why it's very 0 is because of this picture here. I didn't go into this detail, but so the atom that we are operating, it's not really a qubit. It's almost a Q-trit. So there are 3 energy levels that we care for. There are 2 in the ground state for this. These are the hyperfine split states. That's where we keep memory. And there you have this Rydberg state that is the highly polarizable. If the atom is not highly polarizable, there's no dipolar interaction. There's no van der Waals interaction going on. Mm-hmm. So if you had an ion trap, it's an ion, right? It has charge. So you don't turn Coulomb off. Like Coulomb interactions was on even before Coulomb. Right. But here, van der Waals interactions, they can be turned off independent of van der Waals' opinion. So it really depends on how polarizable the material is, and the material will only be polarizable if I shoot laser and excite it. So it's really like a factor of maybe 10,000 or something order like that. The difference between
and
the
say magnetic field of Earth or whatever, this is all irrelevant, right?
So for a different reason, in the hyperfine states, we are putting them in clock states. So they have this kind of magnetic quantum number n equals 0. So as the fields drift, then that guy doesn't really care. Yeah. Cool. Let's move on. Cool. So what are the products that we have right now? We have Aquila. Aquila is an analog quantum computer. We're going to talk a lot about it right now. This stuff that you have been seeing, it's really focused on our gate-based devices that we are going to launch basically this year. I know that the year is ending, but it's not done. And the first of these machines is going to be operating out of Japan next year. But I wanted to take a moment to talk about Aquila because it's really the jewel of the crown today, right? It's a machine that is accessible, it's available to everybody. So Aquila is a 256 qubit machine. We can operate up to 256 qubits because if you want to operate only 10, you can operate only 10. If you want 20, you can 20. It's really a user-defined thing. And it has this analog FPQA architecture. We can discuss a little bit what that means, but it basically means that you can program the connectivity of these atoms a priori. You cannot program as the calculation is happening, but you can define them a priori. And the FPQA stands for Field Programmable Qubit Array. It's like FPGA, Field Programmable Gate Array, but with qubits. And it's on Amazon brackets, so everybody can access it. The cycle, I will try to not go into too much detail about the cycle so that we have more time for other fun stuff, but it basically involves you tell the system what you want it to look like. We load a MOT, a magneto-optical trap. It's a trap, so guess what? It holds things based on optics and magnetism, magneto-optical trap. All the acronyms work. It's going to pick up those atoms. You're going to shape your light. You're going to pierce that cloud with that light, and these atoms are going to be cooled down. So when they see the light, sometimes they get stuck, and it's not all the time. It's going to be like 60% of the time correct, and that's not a good computer, right? You're going to be very angry at me if you see that. So what we do, we create extra reservoirs. You can see them on the side here. We're going to take a photo. That's what this imaging is doing. We're going to see where atoms are missing, and we're going to take the reservoirs that also were loaded stochastically, and we're going to slide them in place. So they go in place, and now we have something that looks more like a processor. You can see that this has some errors. I'm being honest here. So there is about 99.5% chance of putting atoms in the right place. 99.5 looks good, but it's per atom. So if you want to do 100 atoms, it's 99.5 to power 100. That, you can do the math, right? 30% or something. But still, you are going to do your repetitions, and they're not too expensive. So we sort them in place, image them to make sure that they're right there, and then you do a calculation. This calculation is going to last about 4 microseconds within a coherence time that is about 7 to 8 microseconds. And you measure in the end, and what you see is a figure like this, where atoms shining are in the ground state. This is a fluorescence imaging. Atoms that are dark are excited into this Rydberg state. Actually, they flew away, technically. You are not going to get an image like that, because otherwise you're going to be like looking at photography to do your calculation. It's going to be bad. What you get is just a bit string of ones if they are shining and zeros if they are dark. Shining is the ground state, so 1 is in the ground state, which is your logical 0. I did not decide for that. Don't blame me, but it's a fact. So let's have some fun. I don't know if you ever saw a quantum computer operate. I think that one thing that is a lot of fun with neutral atom systems is that you can actually see this with your own eyes. Right? If superconducting systems, it's kind of just electric signals. This is also signal because it's a camera, but you can see it. So this is a video of our QView. That's what our folks, if you come visit us at QuEra, you'll see this running on the wall because people are looking at this all the time, doing kind of calibration or something. And you see on the left atoms before sorting, atoms after sorting. Now you learned that atoms that are far apart are not interacting. So you can see that these guys are far apart in comparison with these ones. And I'm doing here a 2-pi pulse. So if you're okay with your block sphere, shining means pointing in the north. And then 2-pi means rotate around the x, let's say, back to the north. So you start shining, you finish shining. You're not crazy. You're seeing this blink, right? You're definitely not crazy. You probably have heard that there is such a thing called errors in your quantum computer. So welcome errors, right? Sometimes they're not supposed to be shining. They're supposed to be shining, but sometimes they are not. Right? They're a little stubborn. An atom that was excited might have decayed, and now it's shining, although it was not supposed to be shining. And everything else can be happening. So this is super cool for me that you can really see with your own very eyes how quantum computing works. I did one. The next one is on you. I'm doing another rotation by another angle. It's still around the x-axis. If you never saw this, if you already saw this, then don't spoil for your friends. How much do you think we are rotating by? Don't be shy. So I'm going to rotate this qubit. I'm rotating it by an angle, right? And I'm measuring after the rotation. The question is, what's the angle that I'm doing in this case? Ah, too bad, huh? Yeah. Probably the lights, but it's okay. No, well, 1, 2, 3, control, lights, off, go. No, didn't go. Really, you can see, I can see from here. I know we're gonna do this. It's important. It's pedagogical. It's ludic, and like, you're not gonna be off the hook. So oh, I see. We have a, but probably we need the lights really. Okay. You're gonna spare me a couple minutes in the end extra because of this, but it's gonna have been worth it. Meanwhile, you go thinking. Is it better? Can you see a little better now? Yeah. Right here, blinking. Almost everybody's shining, right? But sometimes it's blinking. I try again. Good. Okay, so by how much we are rotating? Pi over 2. Who guessed pi over 2? Guess right. This is what's sometimes you know as a Hadamard gate. Now, for me, I get emotional when I see this because countless times I have written in my notebooks 0 plus 1 divided by square root of 2. Countless times. And this is what it means. Right? Like sometimes it's 0, sometimes it's 1. Half of them are 0, half of them are 1, give or take. Right? So this is what quantum mechanics means. Like is when you try to put a bunch of this together, you see about half of them in one state and half of them in the other. Not only this is a processor, it's a parallelized processor. We are doing like 36 measurements at once at every kind of frame. So this is pretty cool. Aquila, you can do that kind of fun, but that's kind of single qubit, not so interesting. Aquila does not operate digital gate-based quantum computing. This is what you are maybe familiar with, like this single qubit and 2 qubit gates. Aquila does something that is on the right-hand side, on your right-hand side, exactly, which is to operate on all qubits at once, right? So if you operate on all qubits at once, I like to call this a many-body gate. It's not it's not 2 qubit gate, it's a many-body gate. And you're controlling that continuously in time. If you're controlling continuously in time, you're just evolving, and evolving is Schrödinger equation. Schrödinger equation is controlled by Hamiltonian. So all you need to do is to know the Hamiltonian. This is universal, but it's not efficient. Every gate you have to control very precisely. The other side is efficient. You only control this thing globally, but it's not universal. It's very hard to make universal because to make it universal, you would need to have a Hamiltonian over there that you can basically control everywhere. And this is like a SU or U2 to the n for n qubits transformation. You're not gonna control that easily. So,
since you challenged us, can I challenge you? So how large of a cat you can create? Because in these pictures, of course, if you see 10 atoms doing the same thing, you have like a 10 atom cat state or whatever, this GHZ state.
oh, the GHZ
So
state.
how large you can realistically do?
I think that the largest GHZ that we have done is on the 20s of atoms.
So you can see 20 atoms blinking together, right?
Yeah. I think that those have been the largest that we have done.
And can you make some picture out of them, like
just
not in a line, but have some nice star or whatever, and then you show like quantum dance or something?
Should try to do that. We'll discuss that. But I think it's in the 20s. Yeah. Probably we can do better, to be honest. But GHZ is a little more complicated. So how do you overcome the fact that this thing is not universal? Is by giving you freedom to choose where the atoms go, right? So the atoms can be in a square lattice, they can be in a Kagome lattice, they can look like the world coast, if you forgive me a little bit for the imagination, right? And you can really make these things do a bunch of things and play around, right? I think that one of the first things that the folks had done at Harvard was to do a little Super Mario animation, which was pretty awesome. We did Hello World. So again, field programmable qubit array, you probably encode with the atom positions. How do you control this is going to be where we are not going to do a coding school today, But basically, you control energetics. Just like what's the energy that this qubit has, how much is the energy that that other qubit has, how do they interact by proximity, and then you go. That's the summary. What can you do with that? You can do a lot of things. Now, I know that there is like a pattern appearing. Here I have to talk about our closest friends, such as politics, right? But there's been a lot of other groups that have been doing this across the world, not only locally here. In France, there's a lot of good work. In Germany, there's a lot of good work. Chicago, California, everywhere. But these are some of the things that have been done that have kind of really put this platform in the news, right? So we have done quantum phase transitions, critical systems, critical dynamics. We have figured out that the more dynamics you look at, you kind of find out new things that have never been seen before, like many-body quantum scars. If you do frustration, you can see spin liquids. And if you play a little bit between the frustration and order, you can do actually optimization. Optimization like a standard optimization. So I'm not saying that these optimizers are better than your best classical optimizers, but I'm saying that when you look at how these things scale with the number of qubits and number of problems, problem complexity, you see a square root divergence between kind of a classical comparable method and this one, which means that quantum mechanics is really making a difference here. It's like a Grover type of speed up. So kind of cool. And definitely those were good fruits, but not the only low-hanging fruits. There's been a lot that's been done with Aquila. So when I first put these slides together, was all work in development. And by now, I don't have the references, but basically everything is published. So there's a lot of people working on this. It's time that I create a new slide for this with the even newer things that people are doing, get permission to tell other folks what people are doing with this. But we are solving problems in machine learning space. We are solving problems in the high energy physics space. We are solving problems in the condensed matter / chemistry space. We are solving really problems all around, and with entities that include university, that include academia, that university and academia are the same. Include FFRDC, so research labs, DOE labs, and also with the kind of external users, kind of commercial users. This is not the end. This may be the end if you want it to be the end. I do have a few more words. But we programmed this using a software called Blockade that you can just package add on if you like Julia. You can pip install if you like Blockade. It's not enough a release anymore. I should update that. And you can access this on AWS. There are credits for researchers. It's a process, but it's possible to get them. I just wanted to finish a little bit with a few words on really how we are helping strengthen the regional ecosystem, right? So we really think that tech can be used to develop economy, right? Basically, commercialization and investment are connected with product creation. Then those are also connected with workforce development, and they feed each other, right? So we have been working a lot with folks in Massachusetts. We have this concept that we call the Quantum Center of Mass, because it's such a great name. And that is really kind of the umbrella of activities that at least we at QuEra are looking at collaborating with universities and in particular with the government of Massachusetts. Government of Massachusetts is really wanting to focus efforts on the western part of the state that is much poorer than the eastern part of the state. Nevertheless, they form a very interesting corridor between kind of from New Hampshire down to Connecticut, and from New York all the way to here Boston and to Rhode Island. So it's a pretty well-placed space without so much tradition in quantum, despite the kind of universities like Amherst. And we are really trying to work together to bring attention and bring folks to work there. You'll certainly be hearing much more about it. One of the things that we are doing is to really kind of create a user facility for access to quantum computers. We are hoping to have like user groups to think about how to use this best, have a kind of an open access structure so that the researchers in the area will have a kind of facilitated access to quantum computers. And anyway, the plan is quite comprehensive, and with support of people like David here, we have been engaging with universities, including BU, So we're really, really hoping that this is going to flourish into something that's going to be good for everyone. So now it's the end. You know the spiel. It's the same as before. If you want to access Blockade, you can find it there. You can install it very easily. If you want to talk more to QuEra, that's my connection. We are hiring a lot. If you care about any of this, reach out. And if you want access, it's on Bracket. So thank you very much for having us.
Sorry, but this time I'm kind of more about students. So there are these opportunities you mentioned, but are there like some internship opportunities?
Yeah,
so
yeah.
Students interested,
Absolutely.
Okay.
Absolutely. As well, we have hired interns from undergrad. We have hired interns for grad school. There is grad students tend to have some advantage on the recruiting process, but we have hired all across, and like we have really a bunch of different departments that we have different demographics as well. So I could hear it. I could hear it.
Now you can hear. Oh, wow.
I can still hear it.
I won't yell. I'll do it silently. Yeah, I mean, the coherence time is what, a microsecond you said, is that right?
So depends on which states you're using. Aquila uses ground and Rydberg to,
Yes.
to encode information.
Right.
But the Rydberg state, as we discussed, is very polarizable. So it's very sensitive to fields all around, straight fields and everything else. So even the lasers that are holding the atom. If you are doing, which is one of the reasons why we actually turned the lasers off, and when exciting. If you're doing gate-based computing, now we are using the hyperfine states. The hyperfine states, again, they are in this kind of clock states. They are much more protected. The coherence time is about a second and a half.
Oh, really?
To start, I believe.
So, I mean, you have an architecture, but if you look at classical computers, the transistor was invented a long time before silicon. I mean, is there a future for this architecture in another material, or is you think this is?
I mean, there are other atoms that are competitive. Strontium is a competitive atom. Ytterbium is a competitive atom. So far as I can tell, we like rubidium. I haven't heard of a reason why rubidium wouldn't work. For every advantage, there's a disadvantage on the other.
I mean, silicon got stuck after a while as well, so.
It's okay.
Since you mentioned your competitors like Google and IBM.
Google is one of our investors, so.
Okay. Could you then comment to different platforms and advantages and disadvantages?
I can comment under the understanding that the camera is recording. I'm not an expert on all the other techs, so whatever I say is based on my current understanding, and which might be limited, and I definitely don't paint one as being better than the others. Right, so each of them have advantages and disadvantages, right? So my challenge with superconducting systems is that they are pretty bulky. There are a lot of control lines that go into each of them. So whenever I see the cryostat, I never think of the chandelier. Everybody says the chandelier, it looks like a chandelier. For me, I think of the predator because there's the hair, right, coming out of it. So how many cables can you really fit on that thing? So you need a solution for those cables. I'm not saying that there's no ideas for that. I'm saying that that's something that is blatant for me, that needs to be solved. These guys are also big, and they are manufactured, so no two of them are equal. Not only no two of them are equal, but whenever you hit them up, when you're operating, you always hit them up, defects move around. So you have to recalibrate that thing, because in a couple hours from now, the qubit that you had is a different qubit. To the point that some folks think that to be able to operate a superconducting machine, you have to put it into in a mine under the ground so that it's isolated from cosmic rays. So if you clean those very well, very, very, very well, I don't know if you're going to make a quantum computer, but maybe you find dark matter. The ions they have other challenges. Today, ions are kind of really the state of the art, like best fidelities, and they are a little slower on the clock rates, just like us. But they have some flexibility on connections between different ions, etc. The problem is that they rely on emotional degrees of freedom. That as you put more and more and more atoms, they get very crowded, and there's a lot of crosstalk. And it's very hard to make this kind of a two-dimensional system. So it really becomes like a kind of 1D platform. So scaling the number of ions is pretty hard. You see that today, like, people can't put more than kind of 50 ions together, while we are easily operating over like hundreds of them. So those are some. The fact that you cannot turn off the interactions also is important, because the crosstalk is always going to be there. So photonics is a different one, right? You lose photons. Photons disappear. To be able to do photonics seems like you need to really have new materials that are kind of sometimes never being seen. So seems like you need a little bit of a magic wand to make that happen. But if you do, it could be pretty good. So all of them have pros and cons, right? Like for us, you need to be able to replenish the atoms, because again, it doesn't matter how you measure them, sooner or later there's a background gas, an atom, something's going to collide with your atom, it's going to fly, you need to put it back, right? The clock rates, you do need to improve those clock rates however possible, although the fact that you have this kind of non-local connectivity allows you to leverage things like clock rate doesn't really matter as much when you have a logical system. Like if you have logical operations, you are asking about the logical clock rate. And that's a composition of kind of connectivity, the speed of each operations, but it's not just the speed of operations. So there are lots of tricks that you can get away with. And manufacturing, right? Manufacturing, this is pretty hard because it's like a very fine-tuned mirrors. We can't do it with a person there right now. So there's some balance.
Hi, I just want to ask for like a clarifying question about, since you just mentioned the logical qubit, right? Like, how do you define the logical qubit? Is that like just like in your presentation? Is that just gonna live forever, or is gonna be
no, definitely not.
Longer coherence to individual physical qubits?
It's so coherence can go into it, definitely can go into it, because if you encode information in that qubit and wait long enough, it would kind of decay, right? But then if you can keep correcting, you can keep the information revived in it, so you can keep it alive. But no logical qubit is a perfect qubit, right? So in fact, the larger is your patch, the kind of the longer, the better the coherence is going to be if your code is good. So there is always going to be a limitation to how many operations you can do before errors catch you up, right? And so these logical qubits, they are very rudimentary so far, meaning that there's very few things that you can do that you see a better performance with them instead of if you had used the kind of individual qubits to encode information. But we're starting to see machines all across the industry showcasing that you can operate patches, groups of qubits together to get better performance than you had individually. And the interesting part is that this improves exponentially. The more qubits you use, you get exponentially better. While if you try to fine-tune a single qubit, it's exponentially harder to get an extra 9 over there.
So for the case in your presentation, it's the same, like when you mentioned the logical qubit.
Yeah, absolutely.
Okay.
Absolutely.
What does 99.5 mean? That per second,
So,
I don't even know how to think about that.
so there's the 99.5 fidelity, in which case means that you try to entangle these guys. Let's keep this like the simplest way, right? I try to do an entangling operation in which one atom being the 0 or the 1 is gonna make the other atom pick a phase or not. Okay, and if you did that 100 times, half a time it would go wrong.
Go wrong
Right. it's not gonna flip. It's gonna do something else other than what you're expecting it to do. Sorry. Well, not during the calculation, right? Because while calculation is happening, you cannot measure. If you measure, the information becomes classical. So in the readout, in this case, you're always getting 0 or 1. You're no, you're gonna get a 0 or 1, but that's only you. So with that 0 and 1, you only pick up the kind of the bit flip errors. So if you want to figure out if there was a phase, you have to kind of rotate the qubit before you measure and kind of repeat the experience many times to see if errors are appearing. That's the problem, right? You cannot copy a state. So you can't really. You only know that something came out wrong in the end of your calculation, but kind of fidelity protocols, fidelity estimation protocols, they exist, and you can kind of do the same operations with many qubits in parallel, many pairs of qubits in parallel, and characterize those gates.
So just the last part of understanding this. So can I get 2 1s? I mean, if it flipped wrong.
You can get 2 1s. You
and then
could get 2 1s.
That's an easy way to detect that there's a mistake.
Yeah, you could get 2 1s. The short answer is yes. In principle, yes. Yeah.
I have a bit of a clarifying question. So you said the way these work is you have these 2 reservoirs on the side and your actual quantum computer in the middle, and you blast it with laser and it lights up certain ones and doesn't light up certain other ones, right? Excites. And then the ones that are supposed to be excited but didn't get excited, you move them from the reservoir into your actual quantum computer section, right?
So yeah, that's to set up the processor.
Yeah.
Right, that's before calculation is happening.
So would that mean this works a bit like a battery where like when those reservoirs deplete, you have to get a new quantum computer bit? Or is it more like a rechargeable battery where you replenish those reservoirs and keep going?
Right, so for Aquila, here, let's try to get to Aquila.
Yeah.
You only do this once. In the beginning of your calculation, right, you're gonna look if your atoms are in the right place, you're gonna have some extras, and then you're gonna put them in place, and now you're gonna do your whole calculation. In the end, everything flies. So we are the fastest makers of quantum computers in the world. We can make a new quantum computer every 300 milliseconds, right? Okay. But the problem is that it's like catering, right? You eat on plastic paper. In the end, you throw the computer out.
Okay.
so you have to make another one.
Okay. Okay.
Right now, if you're operating a gate-based machine, you might be wanting to measure some of the qubits while you don't measure others. If you lose those, you certainly have to replenish. So you need to have another reservoir that you can keep adding atoms, so that you can operate long enough. That's a different mode of operation.
Just more like a disposable computer versus like a computer I can carry around with me everywhere.
Yeah, if you want. Yeah.
So if you were gonna bet on what technology was ultimately you want error-corrected gates because it's universal. The fact that you can move these atoms around and make a new computer in however many milliseconds, right? Is this the technology that you should be experimenting with the design of gates, right? Because otherwise you have to make new chips every time, right?
I think so. Like the capacity to empirically test kind of error correction protocols and change them, and like a lot of kind of making new neutral atom machines goes into the software side. You can change a lot of it just by software, and certain parts of the tech requires an actual new module. But once everything is there, there's many things that you can try. So I think that, to say the least, is going to give us a good idea of what's the best way of making a quantum computer. 100 years from now, I don't know that we are going to still be using this, but I'm pretty confident that whatever it is that we're going to be doing is going to be very well informed by what we have done with this tech. I think that it's fair to expect.
Yeah, I don't know if you're allowed to disclose, but okay, I understand how everyone can, log on and have access to this. But in terms of the physical thing, how many do you have? Is this all one
Aquila is one machine
Okay.
so far. We don't have a second one.
Okay.
The machine that this Gemini machine, it's going to Japan,
I see.
and it's a one machine that is going to Japan. We have a machine that we're building for the UK, which is not a user machine. It's a kind of a hardware development machine.
And that's the 256 qubits?
All of this operates around 256 qubits. And we were just awarded again by the state of Massachusetts to build one for the state.
Oh, got it. And that's going to be in Springfield?
That should be in Springfield and Holyoke, in fact. The MHPCC going to take us many months to build, but we are hoping to be operating that. Did we? Oh, it's the same. It's the same. It might be upgraded in the process, but in principle, it's the same.
But if we log in, we're using your machine here on the side. Like that's the one.
That's this.
Yeah,
this is it. This is it. The same thing that took those photos. Cool. Yeah. And I mean, anyone that comes visit QuEra will see all of this being built. There are other machines for R&D purposes, but the commercial, this is all public information. Yeah.
You have this ability to save a state, right? In a memory, in a sense, and keep it, right?
To some degree.
Yeah,
right.
To some degree. Is it possible to prepare a state, save it, set up a new machine, and then initialize from that state prepared?
Not on Aquila.
Is that, I mean, if we could get state preparation out of the evolution, it would be a huge thing.
I know.
You don't think there's no way to do that with your memory system?
No, so that requires mid-circuit readout.
Yeah.
And I am not yet sure which machine in this pipeline is going to be the first one to show mid-circuit readout for users.
But you're thinking about it, good.
Yeah, absolutely.
Okay. Are there no other questions? This has been pretty exciting, and thanks very much for the great engagement. And let's thank Pedro for a really fascinating talk. There are a few refreshments over here, coffee and cookies, and continue the conversation. Thank you.
I am very easy to find. Okay, so please reach out, and I love helping people, whatever it is that they need to do. So, yeah, seriously.